All right, so you want to understand machine learning algorithms.
Yeah, it's a pretty fascinating field.
It is, and luckily I think this educational overview is going to be a really great place to start.
For sure, for sure.
Um, by the end of this deep dive, I think you'll not only be able to choose the right algorithm, but really get like the intuition behind each one, so you're not just
Yeah,
kind of lost in the jargon.
exactly. And what I think is so cool about it is that you're basically teaching computers to learn without,
Right.
having to tell them every single step of the way.
Yeah. So let's start with the basics. What is machine learning according to this overview?
Well, it defines it as, a subset of AI that deals with these algorithms
Hmm.
that can learn from data. And the key here is that they can then apply that knowledge to new data that they've never seen before.
So it's not just about like memorizing the data that they've seen, but it's about actually learning from it
Exactly.
to
General.
make predictions. Yeah.
It's huge.
It's
Yes,
like giving them the ability to kind of see into the unknown.
it really is. And, you know, think about all the advancements we've seen recently, especially with neural networks.
Mhm.
Those are behind everything from, image recognition to language translation.
It's incredible. And it's all because they can kind of learn these really complex patterns
Right.
from massive amounts of data.
Right.
But let's not get ahead of ourselves.
Yeah. Yeah.
This overview talks about two main types of machine learning,
Right.
supervised and unsupervised. So what's the difference between the two?
So supervised learning is probably what you're most familiar with.
Okay.
And it's kind of like having a teacher, you're giving the algorithm labeled data so you already know the answer.
Hmm.
And it's learning from those examples to make predictions on new data.
So it's kind of like giving it a set of flashcards
Exactly.
with the question on one side and the answer on the other, and it can study the flashcards and then try and answer new questions based on what it's learned.
Yeah, like let's say you're trying to predict house prices. So you would give the algorithm data like the square footage, the location, the number of bedrooms,
Okay.
and of course the selling price of similar houses.
Yeah.
And it figures out how those features relate to the price
Yeah.
and then uses that knowledge to predict a new house price.
Based on its characteristics.
Exactly.
Yeah, very cool. So it's basically learning from past data to make predictions about the future.
Mm-hmm.
And what about unsupervised learning? Is that more of a free-for-all?
Yeah, you could say that.
Okay.
So in unsupervised learning, we don't give the algorithm labeled data. We don't give it any predefined categories. We
Okay.
just let it loose on a data set, and it has to figure out the patterns and the structures all on its own.
It's like giving someone a jigsaw puzzle without the picture on the box and saying good luck.
Right. Or, imagine you gave a child a bunch of different animal pictures,
Mm-hmm.
but you didn't tell them what each animal was. They could probably still group them together based on,
Yeah, what they look like.
what they look like, right? They might put all the furry four-legged creatures together, the birds together.
Right.
That's kind of how unsupervised learning works.
So it's more about discovering hidden patterns and relationships in the data.
Exactly. Yeah.
I see. So I think since supervised learning is kind of like the starting point for a lot of people in machine learning,
Right.
this overview mentions linear regression as one of the simplest algorithms.
Yes, it is.
And a good place to begin.
A great place to begin.
So let's unpack linear regression. What is it?
So at its core, linear regression is trying to find a linear relationship between an input variable and an output variable.
Okay.
So if you think about it visually, it's like drawing a straight line through a scatter plot of data points.
Mm-hmm.
That line represents the relationship between the variables, and we can use it to make predictions.
So if I was trying to predict how much money I'd make selling lemonade based on the temperature outside,
Okay.
I could use linear regression to kind of find that relationship
Yeah.
between temperature and sales.
So you could collect data on how much lemonade you sell at different temperatures
Hmm.
and use linear regression to find the line that best fits that data.
Okay.
And if the line slopes upward, it would mean that as the temperature increases,
Yeah.
your lemonade sales tend to increase as well.
That makes sense. But what if the relationship isn't that straightforward?
Yeah.
What if there are other factors at play?
Well, linear regression assumes a direct proportional relationship between those variables.
Okay.
So it's great for things like predicting sales based on advertising spending or maybe estimating the lifespan of a machine based on usage.
Okay.
But if the relationship's more complex, you'd have to explore other algorithms.
So linear regression is a powerful tool, but not a one-size-fits-all solution.
Exactly. And that's why it's so important to understand these different types of algorithms and when to use them.
For sure. All right, so let's move on to another supervised learning algorithm that's often used for classification tasks.
Yeah.
Logistic regression. So it's like linear regression, but for classifying things into categories.
That's the idea.
instead of predicting like a specific number.
So while linear regression predicts a continuous output,
Okay.
logistic regression predicts the probability of something belonging to a particular category.
Okay. Can you give me an example?
Yeah, let's say you want to predict whether a customer will click on an ad based on their demographics or browsing history.
Okay.
You could use logistic regression to model that the algorithm would learn the relationship between those features and the likelihood of clicking on the ad,
Okay.
giving you a probability score for each customer.
So it's basically like predicting whether they'll say yes or no to clicking on the ad.
Exactly. And based on those probabilities, you could target your ads more effectively to reach the customers most likely to be interested.
That's really cool. So I know there are a lot more supervised learning algorithms out there. What's next on our list?
So let's talk about k-nearest neighbors, often called KNN.
Okay.
It's a very intuitive algorithm. It's easy to understand.
K-nearest neighbors. I like that. How does that work?
Yeah, so imagine you have a scatter plot of data points,
Okay.
and each one belongs to a specific category.
Mm-hmm.
So to classify a new data point,
Yeah.
KNN looks at its k nearest neighbors.
Okay.
So the k data points that are closest to it in terms of their features,
Mm-hmm.
and if most of those neighbors belong to a certain category, KNN predicts that the new data point also belongs to that category.
So it's kind of like judging a book by its cover, or
Oh,
I guess judging a data point by the company it keeps.
that's a great way to put it. Yeah, think of it like this. You're at a party.
Okay.
Most of the people standing near you are wearing football jerseys.
Yeah.
You might assume you're at a Super Bowl party.
Right.
KNN works similarly.
That makes sense. So if I'm trying to classify a new customer as, a high spender or a low spender based on their purchase history,
Right.
KNN would look at the customers most similar to them and their spending habits and
Exactly.
make a prediction.
It's a simple but powerful algorithm that can be surprisingly effective.
This is great. We're really building up our understanding of these different classification approaches. Are there any other supervised learning algorithms we should touch on?
Absolutely. One that's particularly well known and powerful is support vector machines, or SVMs.
Okay. SVMs, they sound kind of intense. What makes them so special?
So SVMs are like the strategists of the machine learning world.
Okay.
They're all about finding the best boundary
Mm-hmm.
to separate different categories of data.
So if we're back to that scatter plot example, they would try to draw a line
Precisely.
that neatly divides those different categories.
Exactly, but they don't just draw any line.
Huh?
They try to find the line that maximizes the margin
Okay.
between the categories, meaning that empty space between the line and the closest data points.
Gotcha. So why is that maximizing the margin so important?
Well, think about it. If your dividing line is right up against some data points,
Yeah.
any slight variation could push them to the wrong side.
Right.
A wider margin just makes the model more robust.
That's like giving yourself some breathing room
Yeah, exactly.
to avoid misclassifications.
Exactly.
Okay. Can you give us an example of how SVMs might be used?
Yeah. Let's say you're building a system to detect spam emails.
Okay.
An SVM could analyze the words and phrases in emails and find the best boundary to separate spam from legitimate messages
Interesting.
and the data points closest to the margin.
Yeah.
We call those support vectors.
Support vectors.
Those are the ones that are really important in determining where the line is drawn.
They're like the boundary guards
Yes, exactly.
of the SVM world.
They are.
So what else makes SVM so powerful?
One of the things that sets them apart is their ability to handle high-dimensional data, so data with lots of features.
Okay.
And they can also use something called kernel functions
Okay.
to create complex, nonlinear decision boundaries.
Kernel functions. Those sound pretty complicated.
They can be, but think of it like this. Sometimes it's easier to separate two groups of objects if you kind of move them into a different space.
Mm-hmm.
Imagine trying to separate a mixture of marbles and ping pong balls.
Okay. Yeah.
It might be tricky to do on a flat surface, but if you pour them into a container with different sized holes,
Right.
they'll naturally separate.
They'll fall through.
Yeah, kernel functions allow SVMs to do something similar.
That's a really cool analogy.
Yeah.
So I'm starting to see why SVMs are considered so versatile.
Yeah.
Are there any other classification algorithms we should know about?
Yeah, there are many more, but let's touch upon one more that's often used in things like text classification or spam filtering,
Okay.
the naive Bayes classifier.
Naive Bayes? Is it naive because it's overly simplistic or?
Well, the naive part comes from the assumption it makes about the data.
Okay.
It assumes that the features are independent of each other, which isn't always true in real-world situations.
Right.
But despite the simplification, naive Bayes can be surprisingly effective,
Oh.
especially for text-based tasks.
So it's naive in the sense that it kind of makes a simplifying assumption.
Exactly.
But how does it actually work?
So imagine you're building a spam filter. Naive Bayes would look at the words in an email and calculate the probability of each word appearing in a spam email versus a non-spam email.
Gotcha.
And then using a mathematical formula called Bayes' theorem, it combines those probabilities to figure out the likelihood that the email is spam.
So it's like creating a dictionary of spammy words.
Yes.
And seeing how many of them appear in a new email.
Yeah, and if the email's riddled with spammy words, it's more likely to get flagged.
Gotcha. That makes sense. So we've covered linear regression, logistic regression, k-nearest neighbors, SVMs, and naive Bayes.
We have.
What other supervised learning algorithms should we add to our toolbox?
So let's talk about one more that serves as a foundation for some even more powerful techniques.
Okay.
Decision trees.
Decision trees. All right. I'm guessing that involves making decisions.
It does think of it like a flowchart,
Okay.
where you ask a series of yes-no questions to arrive at a decision. That's what a decision tree does. It divides the data based on different features, creating a tree-like structure where each branch represents a decision.
I can picture that. So it's like playing a game of 20 questions,
Yes.
where the algorithm is asking questions about the data to try and reach a conclusion.
Exactly.
Can you give us an example?
Yeah, imagine you're creating a system to assess the risk of a heart attack.
Okay.
You have data on people's age, blood pressure, cholesterol levels. Whether or not they smoke, the decision tree might start by asking, is the person over 50?
Okay.
If yes, it goes down one branch. If no, it goes down another.
Right.
Each branch would ask further questions,
Okay.
leading to a final classification of high risk or low risk.
So the goal is to find the best questions to ask in order to separate the data effectively.
You got it. It's like the algorithm is playing detective.
Right, trying to crack the case.
Yeah, trying to figure out who's at risk, who isn't.
Exactly. And so while a single decision tree can be helpful, I'm guessing things get even more interesting when you combine multiple decision trees.
They do. That brings us to the world of ensemble algorithms.
Ensemble algorithms. Okay, so that's like a team of decision trees working together.
Yeah. You could say that ensemble algorithms combine multiple models to create a more powerful and robust predictor.
Gotcha.
And one popular method is called bagging, short for bootstrap aggregating.
Bootstrap aggregating. That sounds very self-sufficient.
It is. So imagine you have a big bag of data.
Okay.
Bagging creates multiple smaller bags by randomly sampling data points from the original bag. Then it trains a separate model on each of these smaller bags.
Okay.
And finally, it combines the predictions from all those models to make a final prediction.
So it's like creating multiple mini experts
Right.
and having them vote on the final answer.
Exactly. It's like crowdsourcing the decision-making process.
I like that.
A famous example is the random forest algorithm.
Random forest. So it's full of randomly generated decision trees.
You could say that a random forest combines many decision trees, each trained on a different random subset of the data.
Okay.
And this randomness helps prevent something called overfitting,
Overfitting.
which is when the model learns the training data too well.
Okay. And then doesn't perform as well on new data.
So it's like planting a forest of decision trees
Yeah.
with different perspectives and then letting them all have a say in the final prediction.
That's a great analogy. And because each tree is trained on a different subset of the data, the overall model is more robust.
Right. It's like having a diverse team of experts
Yes.
all working together to solve a problem.
Yeah.
So what other types of ensemble algorithms are out there?
Another important one is called boosting.
Boost.
So unlike bagging, which trains models in parallel,
Yeah.
boosting trains models sequentially. Each new model is focusing on fixing the mistakes made by the previous models.
So it's like a chain of experts where each one specializes in correcting the errors of the one before them.
Exactly like a relay race where the batons pass from one model to the next.
That's a really good way to visualize it.
Yeah, this sequential approach can lead to higher accuracy,
Okay.
but it can also be prone to overfitting if it's not carefully tuned. Got it. So bagging is about combining diverse perspectives. Boosting is about refining the model step by step. What are some specific boosting algorithms?
So some popular ones include AdaBoost, gradient boosting, and XGBoost.
Okay.
They all use different techniques to improve the model sequentially, but the core idea remains the same.
Gotcha. This has been an amazing journey through supervised learning algorithms,
It has.
from the simplicity of linear regression to these really powerful ensemble methods.
Yeah.
It's incredible to see how these algorithms can learn from data and make predictions.
It is.
But I'm curious about neural networks. They seem to be all the rage these days.
They are?
What makes them so special?
Well, neural networks have definitely taken center stage in the AI world, and they're a powerful type of machine learning algorithm that's inspired by the structure of the human brain.
So they're basically artificial brains.
Well, it's not quite that simple,
Okay.
but the analogy is helpful.
Yeah.
So neural networks are made up of interconnected nodes or neurons organized in layers. And these neurons process and transmit information, allowing the network to learn complex relationships in the data.
Okay. I'm intrigued. Can you walk me through how they work?
So to understand neural networks, let's revisit logistic regression for a moment.
Okay.
Remember how we talked about it predicting the probability of something belonging to a category?
Yeah, like predicting whether a customer will click on an ad.
Exactly. Logistic regression is great for simple relationships,
Okay.
but it struggles with more complex patterns. So think about trying to recognize handwritten digits.
Yeah.
There's so much variation in how people write
Right.
that a simple linear model would have a really hard time capturing all those nuances.
You would get confused.
Yeah, and this is where neural networks excel.
So neural networks are better at handling messier real-world data.
You could say that one of the key differences is that neural networks can learn features from the data automatically.
Okay.
They don't need us to explicitly define the features like we did with logistic regression.
So they're kind of independent.
They are. So let's stick with that handwritten digit example.
Okay.
A neural network with hidden layers might learn to recognize features like horizontal lines, vertical lines, curves, and loops
Gotcha.
in the digits. And these features, which we might not even be aware of,
Right.
then help the network classify the digit correctly.
So the hidden layers are like the network's own internal feature engineers.
Yeah, a great way to put it.
They're working behind the scenes to try and find the best way to represent the data.
Exactly. And the more hidden layers the network has, the more complex the features it can learn.
Okay.
And that's the essence of deep learning.
Deep learning. So it's like having this team of super sleuths
Yes.
all working together to try and crack the case of what the data means.
Exactly. And deep learning has revolutionized so many fields, from image recognition to natural language processing. It's powering self-driving cars and voice assistants and all sorts of things.
It's incredible. It sounds like neural networks, especially deep learning, are kind of pushing the boundaries of what's possible with AI. This has been a fantastic exploration of supervised learning.
It has.
But this overview also mentions unsupervised learning. Are you ready to kind of delve into that realm?
Absolutely. Unsupervised learning is where things get really interesting. You know, it's like exploring uncharted territory,
I like that.
discovering hidden treasures in the data.
I'm ready for a treasure hunt.
Let's go.
Okay, so where do we start our treasure hunt in unsupervised learning?
Let's start with clustering.
Quick clustering. So is that like sorting your laundry into different piles, like socks, shirts, towels?
That's a pretty good analogy.
Okay.
So in clustering, we're trying to find groups or clusters of similar data points within a data set.
Okay.
The key difference from supervised learning is that we don't know what those groups are beforehand.
I don't have those labels.
We don't have the labels. There are no predefined categories to guide us.
So it's like giving someone a box of Legos and saying, figure out what you can build.
Exactly. Or imagine looking at a scatter plot of data points. But this time you don't know anything about their categories.
Right.
A clustering algorithm would try to group those points based on how similar they are, maybe by how close they are to each other, or some other measure of resemblance.
Okay, so it's about finding those natural groupings in the data, the ones that make the most sense, based on their features. So how do these clustering algorithms work?
Well, one of the most popular algorithms is called k-means clustering.
K-means, does the K stand for the number of clusters we're looking for?
Yes, you got it.
Okay.
So we tell the algorithm how many clusters we want, that's our K, and it tries to group the data accordingly.
Okay, so we give it a target number of clusters, but how does it actually go about grouping the data?
So imagine it's like a game of capture the flag.
Okay, I like that.
You start by randomly placing K flags on the field. Those are our initial cluster centers.
Oh.
Then each data point runs to join the closest flag.
Okay.
After everyone's picked a team, you move the flags to the center of their respective groups.
Okay, so the flags reposition based on where their team members are.
Exactly. And then players can switch teams if a different flag is now closer, and this process continues until everyone settles down.
So we end up with K clusters, where the data points within each cluster are more like each other than they are to the points in other clusters.
Exactly. It's a pretty simple concept, but a very powerful technique.
So are there other clustering algorithms besides K-means?
There are quite a few. Some algorithms, like hierarchical clustering, don't require us to specify the number of clusters beforehand.
Oh, interesting.
They build a kind of family tree of clusters, allowing us to see different levels of relationships in the data.
Oh, so we can choose how granular we want our clusters to be.
Yeah, exactly.
Cool.
And then there are also algorithms like dbscan that can handle clusters with irregular shapes and do a better job of dealing with outliers.
Outliers.
Those data points that don't seem to fit in anywhere.
Okay.
It's especially useful when those clusters aren't neatly separated.
Right. It's like finding constellations in the night sky.
Okay.
They're not always perfect shapes.
Yeah.
But we can still group those stars together based on, proximity and stuff.
Exactly.
Yeah.
So clustering is a really powerful tool for finding hidden groups in your data.
This is great. So I'm ready to explore another area of unsupervised learning. What's next on the list?
Let's shift gears and talk about dimensionality reduction.
Dimensionality reduction. That sounds like something straight out of a sci-fi movie.
It does, but it's more like decluttering a messy room.
Okay. I like that.
So in dimensionality reduction, we try to reduce the number of features or dimensions in our data set while still preserving as much of the important information as possible.
Okay. I'm all for decluttering, but why would we want to get rid of features? Isn't more information always better?
In theory, yes, but in practice, too many features can make it harder to find meaningful patterns.
Right.
Imagine trying to find a specific book in a library with millions of books, but no organization system.
Right. It'd be overwhelming.
It would be overwhelming. Dimensionality reduction helps us simplify our data and make it more manageable.
So it's like creating that cataloging system for the library so we can actually find the books we need.
Exactly. Too much clutter can just make it hard to focus on what's important.
I see. So how do we actually go about reducing the dimensionality of our data?
Well, one of the most popular and powerful techniques is called principal component analysis, or PCA.
Principal component analysis.
Yeah.
Okay. That sounds very official. What's the principle behind it?
Imagine you're looking at a cloud of data points.
Okay.
PCA tries to find the directions in which the data is most spread out or has the most variance.
Okay.
These directions are called principal components. Think of it like finding the longest and widest dimensions of a box.
So it's about finding the axes along which the data varies the most.
Exactly. And the cool thing is that these principal components are often combinations of the original features.
Okay.
And we can rank them by how much of the variance in the data they explain. Often just a few principal components can capture a surprisingly large percentage of the total variance.
So we can condense the information from many features into a smaller set.
Exactly.
Without losing too much information.
Exactly. And that can make our data much easier to work with.
Right.
And it can even improve the performance of machine learning models.
Wow. So it's like distilling the essence of the data
Yes.
into a more concentrated form.
Exact.
Can you give us an example of how PCA might be used?
Yeah, let's say you're working with image data.
Okay.
And each image is represented by thousands of pixels.
Right. That's a lot of features.
That's a lot of features. PCA could help you find the most important patterns in those pixel values.
Okay.
And represent each image with a smaller set of principal components.
So instead of having thousands of pixel values,
Right.
we'd have a smaller set that capture the most important visual information.
Exactly. It's like compressing a large image file without losing too much quality.
Right. Very cool. So we've talked about clustering. We've talked about dimensionality reduction. Are there any other key concepts in unsupervised learning?
Those are the main highlights. Unsupervised learning is really all about letting the algorithm take the lead.
Right.
And discover the hidden structures in the data.
It's about exploration.
It is. It's a world of exploration and discovery.
This has been a really eye-opening journey.
It has.
We've gone from supervised learning to unsupervised learning, uncovered a whole treasure trove of techniques.
Yeah, and what's even more exciting is that machine learning is constantly evolving.
It is.
There's always something new to learn and explore.
Speaking of new discoveries, what are some of the things on the horizon of machine learning that have you particularly excited?
Yeah.
I know we've only scratched the surface here. What would you say is a good next step for someone who wants to keep learning?
Well, the source actually mentions a really great resource, the scikit-learn cheat sheet.
Oh, yeah, I remember that.
Yeah.
And they talked about how it can help you figure out which algorithm might be the best for your specific problem.
Exactly. It's a really helpful visual guide that can help you navigate the landscape of algorithms and make more informed choices. Yeah. Right. And plus, scikit-learn is a powerful Python library for machine learning, so it's a great tool to add to your skill set.
So armed with what we've learned in this deep dive and that cheat sheet, I feel like anyone could start experimenting with different algorithms.
Absolutely, and that's the beauty of machine learning.
Yeah.
It's a hands-on field. The more you experiment and play with different algorithms and different data sets, the more you'll learn.
It's all about diving in and getting your hands dirty with the data.
Exactly.
And seeing what you can create. It reminds me of like when I first started learning to code.
Yeah.
It can feel intimidating, but once you start building things, it's so much fun.
I totally agree. And that sense of playfulness and curiosity is so important in machine learning because it's a field that's always evolving. You need to be comfortable with experimenting and trying new things.
Speaking of new things, what are some of the areas of machine learning that you're most excited about? What's on the horizon?
Well, one area that I think is really fascinating is the development of algorithms that can explain their decisions more transparently.
Okay.
You know, as we rely more and more on machine learning for things like medical diagnoses or loan approvals,
Right.
it's becoming really important to understand how these models are arriving at their conclusions.
Yeah, explainable AI is becoming crucial, especially in those areas where the stakes are high.
Exactly.
What else has caught your eye?
Another trend I'm excited about is the rise of federated learning.
Okay.
So it's a way to train models on decentralized data without compromising privacy.
Interesting.
Imagine being able to train a really powerful medical diagnosis model using data from hospitals all over the world without ever having to actually share that sensitive patient data.
Yeah, that sounds like a game changer, especially in healthcare or finance.
It really does.
It's amazing to see how machine learning is not only advancing in terms of its capabilities,
right,
but also addressing ethical and societal concerns.
It's a really exciting time to be involved in this field.
It is.
And I think as machine learning continues to evolve, it's important to remember that it's not just about the algorithms themselves.
Yeah.
It's about how we use them to solve real-world problems and make a positive impact.
Well said. This has been such a rewarding deep dive
Yeah.
into the world of machine learning algorithms.
Yeah.
I feel like I've gained a solid foundation, and I'm excited to explore more.
I know, me too. It's been a pleasure exploring this world with you.
Likewise. And to all of our listeners, thank you for joining us on this journey. Keep learning, keep experimenting, and who knows, maybe you'll be the one to create the next groundbreaking machine learning algorithm. Until next time, happy exploring.